All right, so the next topic in chapter 33 is polarization. Looking back at our electromagnetic wave, this is just one wave, right? It's just one wave from one object moving up and down. But typically there's lots and lots of particles and they're all moving around and they're all sending out electromagnetic waves. And so you get, if I was looking from over here, if I was looking from over here and the waves are coming towards me, not only am I going to see the wave that we're talking about here, where my electric field is basically moving up and down like this, which I'd see that's this guy, this one that's moving straight up and down the y-axis. But I'd also see a wave that had probably its electric field that's going like this, and one that's going like that, and one that's going like this. They're going to be randomly oriented because my particles could be moving and all these different things. So you're going to have all these randomly oriented electric fields. I can't draw the magnetic fields on here as well because it would just be the messiest diagram ever, and it's already fairly messy. But other magnetic fields would be present, and they'd be perpendicular to all of the situation. For this one, the one we actually have drawn, the magnetic field would be like this, right? It would be in the z-axis. That's the one that goes with this first electric field. There's my magnetic field variations. We call this unpolarized light. Basically, it's coming in randomly oriented. But I can put a filter that would cause it to block all but certain orientations of the light. So here's their versions of this right here. You can put a filter there. Usually the filters they look kind of like this. They've got these big, long, stretched out lines in them, although they look mostly transparent. But if you really, really look at them, you can kind of see these lines going, lots of all moving up and down there. It doesn't really matter how they do it, but they essentially only let the light that has a certain type of polarization come through. So here they're showing we have this regular unpolarized light coming in, and then what makes it through the polarizer is only the vertical polarized electric field parts. And they only show the electric field, but we understand that we're also leaving behind the magnetic field. So we have a polarizer that only allows certain oriented waves that can pass through. This is obviously going to decrease the intensity, the amount of energy you're getting. And you can also have multiple polarizers in a row. Like you can have, this is just one polarizer in this picture, but you can have situations where you put more than one polarizer that makes it through. In fact, if you put them completely perpendicular to each other, so here we have unpolarized light coming through, and then we have this. If we have this second polarizer that's perpendicular to the first one, which is not how this is showing, then no light would come through. If we turn this completely perpendicular, we'd have no light that would come through, and you could see that's what's going on in this situation. Is the first polarizer is essentially perpendicular to the second polarizer, and so we're getting zero light that makes it through. To calculate the amount of intensity that gets to make it through, first there's one mathematical thing for the first polarizer, and then there's a different thing we do for the second one. The first polarizer essentially just blocks half the light. The first polarizer, you say the intensity of the light before, you divide it by 2, and half of it makes it through. For polarizers after the first, so in 1, 2, 3, 4 in these pictures, basically the intensity after it is going to be the intensity that came in before divided by this cosine squared of an angle, where this angle is the angle between those two polarizer angles. So let's do a problem, because that really always makes things much more straightforward. So this is the one I want y'all to do, number 33. It shows us what's actually happening. So we have light that's coming in. Back here, this is our unpolarized light, and so we have intensity 0 that's coming in. And then it hits this first polarizer, where it tells me that this angle is 40 degrees. So then I'm going to have intensity 1 that comes out, and obviously intensity 1 is just intensity naught divided by 2. But now the light comes in to my second polarizer, and they tell me that this angle right here, theta 2, is 20 degrees. So intensity 2 should be intensity 1 times the cosine squared of some angle. The angle here is supposed to be the angle between the first polarizer. So let me draw that, let me superimpose that onto here. So the first polarizer, if this is the y-axis, the first polarizer is at an angle of 40 degrees there. So the angle I'm looking for is the angle from between these two, between this line and that line. Let's blow this up a little bit. So let's look at that polarizer again. Oh goodness, I don't want it to have any fill. So here's my positive y. My first polarizer made an angle, oh golly, it's not as bad as I thought it was going to be, of 40 degrees from the positive. That's my theta 1. My second polarizer, actually, if we look at it from down here, this is our negative y. We have an angle of 20 degrees. So the angle I actually want is this angle. And that angle, let me rewrite this someplace else. That angle is 180 degrees minus the 40 degrees and the 20 degrees, right? This whole thing would be 180. So I have 40 plus this angle that I want plus 20 equals 180. And that's 120 degrees. So I2 is I1, which I1 is I naught over 2, times the cosine squared of 120. Cosine squared of 120 is 1/4, and so we get an intensity of 1/8 of our initial. That's after the second polarizer. Now it's coming back in again, and it tells me that this angle is once again 40 degrees. Theta 3 is the same as theta 1. It's the same polarizer. So again, the angle between this and this is still going to be 120 again. We have the same situation we had before. We have 40 and we have 20, and now we have an angle. So once again, now I3 is I2 times the cosine squared of 120. I2 is I naught over 8. Cosine of 120 squared again is going to be 1/4, and so this is I naught over 32. Okay. The last part of these chapters has to do with when light encounters a medium or a material that it's either going to reflect off of or it's going to transmit through. So not absorbed. If it is absorbed, it just goes away. So these are our three options. Or light can get to something, you can either transmit through it, it can reflect off of it, or it can be absorbed. If it's absorbed, then it's just gone. But if it's not absorbed, then we have to figure out where's it going to go now. Where's the light going to go now? When we do this, we generally draw our light as a ray or an arrow. And the direction of that arrow is basically the direction that the light is moving. It's the velocity of its speed direction. If light is reflected, this is the easiest thing that ever happened in physics. The law of reflection, it feels like it shouldn't even be a law. But the law of reflection says if you have an incoming light ray, here we go, our incoming light ray, and it hits this, say, our mirror. So a mirror, generally we draw these hatch marks on the back. This is the non-shiny side. And mirrors obviously reflect light, but other things can reflect light as well. I mean, you and I are reflecting light, and we're still obeying the law of reflection as well. It's just a little bit messier with you and I because we haven't been polished. What happens here is that there's a normal that's moving away from the place where, so the incoming light ray comes in, it hits your mirror at this location. At that place, we draw a normal, which is just a 90 degree from that mirror or the location when it hits the mirror. And then you can make an angle from the light ray to the normal, when we call that the incident angle. Goodness. And then there's also a reflected angle, which is measured from the reflected ray also to the normal. And these two angles have to be equal to each other. Remember that the thetas are measured from the ray to the normal, not from the ray to the mirror or to the plane. And I know here it would come out the same. I could sit there and say, well, there's a phi I and a phi R, and those would also be equal to each other. But there are situations where they won't be equal to each other. If you have a curved mirror, then phis would not be equal here, but the thetas still would be. So we don't use phi. We use theta. So you don't measure to the reflecting surface, you measure to the normal. Number 49 is the problem I'm going to have you guys do with this. I'm not going to do it here. I'm going to probably do that in class. By the way, the first lab that we do on light is going to use the law of reflection and law of refraction. So we'll do some of these in lab as well. If light is transmitted into material, so not a reflection, if we actually have it transmitted, it's more complex. As light passes from one medium to another, it actually bends, and we call this refraction. That's really hard to see. So it's reflection is when it bounces off, and then it's refraction when it bends because it's moving from one material to another. You have far more physical experience with this than you think from the terms of it. A long time ago, Dr. Penny was a lifeguard, and I also grew up with a pool. And back when I was a kid, there wasn't anything else to do, and so we would dive for pennies or we would go to the bottom of the pool. And what you realized was that what you thought something was at the bottom of the pool was not actually where it was. And so this is refraction. It's also when you look through a glass of water and things don't look like they're supposed to be where they are when you look through just the air. It's because the light has been bent as it goes through the water. And this is why also glasses work. And contact lenses, it's why lenses of all sorts work, because light gets bent as it moves into this different material. So it can pass through, but it bends. So the rule says that, so here I've got one guy sitting at the bottom of the pool, and light comes away from this person, and it moves up to basically the interface between the water and the air. And it makes that ray, this light ray that's in the water, makes an angle, again, with the normal. So again, we still have a normal. The normal exists. We want to draw the normal at the place where the light ray hits the interface between the two mediums. And so we have this 90-degree line that extends both up and down into both media. And we have an angle of what the ray makes with the normal in the water. And then we also have an angle of what the outgoing ray makes with the normal in the air. So little a stands for air, little w stands for water. Now, the reason why when I sit there and I look in the pool, if this is me, this is Dr. Penny right there. Dr. Penny. If I'm looking at this child and I see the light coming, I don't think the light has gone and bent. I think that the light has gone in a straight line. So that's supposed to be a straight line. It's pretty close with this right here. And so I see an image. I see the person or whatever I'm looking at further away from the wall of the pool than they actually are. This is an image of the person. It's not actually where the person is, and it's because the human eye is convinced that light travels in a straight line. And so this line of the light that I see outside of the pool, I think it continues down into the pool, and that's where the person is. And again, this is refraction. The physics law that actually goes with the mathematical equation is this, that there's an index of refraction, a little n that exists for every type of medium, every transparent medium. And that number n times the sine of the angle inside that medium. And so for our situation here, we'd have n air sine of theta air equals n water times the sine of the theta measured in the water. The speed of light is c in a vacuum, but in other material it's actually smaller. And so the index of refraction is the speed of light in a vacuum divided by the speed of light in the material that you're talking about. So for water, the index of refraction for clear distilled water is about 1.333. Again, that's the speed of light divided by the speed of light in water. The speed of light in water would then be this. I can basically determine it. It's slower. It's still really, really fast, but it is slower. For air, the index of refraction is very, very close to 1, right, for a vacuum, and is defined to be 1, exactly 1. And so this is extremely close to 1 for air, but it's not exactly. It does move a little bit slower. But generally, we're not going to need more than 4 significant figures, so we just use 1 as the index of refraction for air. Looking at this simple problem I just did, where I say, okay, well, if that angle up here was 35 degrees, and I wanted to know what the angle was in the air, then I can just plug this in. I can say, okay, well, n of air times the sine of theta air is n of water times the sine of theta in the water. N is 1 for air. I want to find this, 1.33 and sine of 35, and I can go through and do the math, and I got 49.9. Y'all can double check that for me if you want. We'll do some more examples of this in class as well. Just some general things here. When light moves into a region, if light is moving into a region where there's a larger n, or in other words, the speed of light is actually slower, then the light's going to bend toward the normal. In other words, so if I have the opposite situation that I just showed with the water, with the light coming from the bottom of the pool, if instead I have somebody at the top of the pool and light is moving away from them down into the pool, and then I'll draw my normal. There's an angle here, and then when the light travels into the water, it's going to bend towards the normal. In other words, it's closer to the normal now than it was up above. Yeah, so this theta water is less than the theta air. That's what I'm saying. It bends towards the normal. Just as we saw before, when it moves into a region with a smaller n, like we had, or a faster speed of light when you go from water into air, then it bends away from the normal. So here, this was pretty close, and then this bent out away from that normal. The angle theta A is bigger than theta water. And we'll do some real-life examples, experiments with this in lab. Okay, so that's what this is here. And that's all I've got for chapter 33. There isn't any more. This is Aaliyah's this is the complete chapter 33. We also have a significant amount of stuff we have to do in chapter 34 for the next homework set.